Lastly, we need to determine the temperature drop across the section F. So across trees, our temperature drop, or delta T, is between from 0.4 to 0.5. Okay, because this is our material F. Okay, so our letter C, solve for temperature drop delta T at material F. Okay, so that is between 0.4 and 5. Okay, so using our equation, so we have Q is equal to delta T. So this is our delta T, or the temperature drop across section F, or from 0.4 to 5, all over the, since we've only a single material here, which is F, you can now say this is all over the R of F. So since we have the value of Q and the value of this RF, we can now directly compute the pressure drop across 0.4 to 5, or across the section F. So therefore, our delta T cross F is just equal to Q multiplied by RF, which is our Q is just equal to 4,557.89 watts times our RF is our RF. Where is our RF? This part here. Our RF is 31.2 times 10 to the negative 3 kW. So our delta T across material F is just equal to 142.2 degrees C. Since this is in the form of delta, we can now use this value, unit 142.2 degrees C. That's it. Okay, let's run through in our given problem. So we have this problem, and we need to determine these three: the rate of heat transfer through the wall, and by this illustration, we need to determine the heat transfer through this composite wall. So we have different materials with different thermal conductivities. And by doing that, we can now see that the flow of our heat transfer is from higher temperature to a lower temperature. So our Q here is from this point up to this point. So we've designate different points from point 1 up to point 5. Okay. Then in order for us to determine this heat transfer through the wall, we've used the concept of the thermal resistance. So by the way, we use the equation, which is our Q, or rate, heat transfer rate, is just equal to delta T over R total, wherein we refer our delta T as from 0.1 to 0.5, from this point up to this point. So we have 300 minus 100 is just 200, and our RT is the total resistance of this whole wall, this from A to F wall. Okay, and using the concept of thermal resistance, we've create another figure showing these resistances. So we have this RA, which is this part here, the resistance of A, and then it is now connected to the parallel wall C, B, and C. So we have this part here, and these walls here is connected to the D and E, so we have this thermal resistance as representative like this, and finally to this single material F here. And if we compute the total resistance using this concept, we can now plot this as RA plus the total resistance of this point, which is this part here, and this point here is this part, and finally this part. Okay. Or if we can refer it to the figure, this RA here is this part here is this part here is the combination of this, and finally this part here is this one. Okay. So to compute to the RT, we've determined the specific values of R from A to F. Okay. And by having that, we can now substitute the value of these R's to our equation RT, to equation 2. And after getting the total R, we can now solve for our Q, or heat transfer through the wall, using our initial equation, which is this one. So by having that, we've come up with the value of our Q, which is equal to this 4,557.89 watts. Okay. And then for letter B, we need to determine the temperature at point 3. The temperature at this point, between this point here. So we designate it as at our point 3. So using our equation, since we already know our heat transfer, and that is equal to the heat transfer all over to this wall, you can now use that value. And since we've only considered up to this point, we can now say that our delta T here is from 0.1 to 0.3 only. So we will only consider this part to determine the value of temperature at 0.3. Okay? And since we've only considered this part here, we only need to determine the R total of these considerations. Okay? So by having that, we plot it using the concept, and we show the resistances RA and the combination of these resistances. And by having that, we've come up with the total RT, and we've substitute it to this part. We only know the value of Q. We've already computed the RT, so now we can now compute the value of the temperature at 0.3, since we know the value of T1. And by having that, we've come up with the temperature of T3, which is equal to this temperature, 261 degrees C. And finally, we need to determine the temperature drop across the section F. So we've only considered this material, or this section, and we've only need to determine the delta T across this material. So we have delta T of 0.425, or at material F. So this is our unknown. Since we already knew the value of Q and our RF, we can now easily find the delta T, or the pressure drop across section F. And by having that, we have delta T is equal to 142.2 degrees C. Okay. So that's all for this given problem. I hope you learned something, and see you on the next video.